So I'm getting ready early before the students get here. I'm going to go through the 6 types of ways to calculate thermodynamic functions like enthalpy, entropy. So I'm just going to list them on the board behind me before my students even get here. Here we go. Got to get this so you can see as much as possible here. And they'll hopefully start rolling in here. I have a lot more room. So I'm going to move those in a second. But I'm going to go through the 6 ways to calculate thermochemistry or enthalpy. Okay, so I'm going to list them right now. So the first way is to just use the stoichiometry. So I don't know how else to write that, but I'll do an example problem of that. I have 6 example problems and 1 of each. So I'll show you those, as we go. They're all right here, brightly colored. There they are. So one of these will be just stoichiometry, meaning calculating delta H. So I'm going to list that one first. A lot of teachers will say that's like a heat of reaction. And it's like some kilojoules per mole. And you can put a number here, depending on the equation of the reaction. So then there's some number here. This could be a number, and then this could be a plus or minus. Okay, so you'll need a balanced equation to do that. All right. Second way is the most common way that we've learned is calorimetry. And that's just Q equals S times M times delta T. They also might see C. So what that is Q is, let me get out of the way. So Q is just heat, and then S is heat capacity, or C, mass, and then change in temperature, okay? And then the third way is using the summation formula. So you've probably seen this before. It's a version of Hess's law that I'm not going to derive because it's too complicated to derive right now in this time frame. But usually it's at standard conditions, okay? And that means that it's at 1 atm and 298 Kelvin, okay, and 1 molar. The next thing is that you will have the moles of the product times the heat of formation at standard conditions of each product, okay? So that's each product in there. Then you subtract it from, and that means summation. Hopefully you know that already. And then moles of the reactant times the heat of formation at standard conditions of each reactant, okay? So again, that little circle means naught. That's how it's stated, like this little thingy. It's NaUGHT, and that means standard states. So again, I'll become closer standard states because I'm still sick from the last time I was on the video. States. That's 1 atm and 298 Kelvin. Okay, and then you could say 1 molar. Okay. All right, that's number 3. Number 4 is using equation. So it's the original version of Hess's law, but they don't have to be formation equations. So it can be any equation. So I'm just going to write it like A and B. Okay. So like A plus B, gives me C, and then maybe C plus, I don't know. Let's just say D gives me E. All right. So you can multiply them. You can inverse them. And so over here, there'll be a heat or an enthalpy. You can call it a heat as long as pressure stays the same. So a lot of times you'll see your chemistry teacher say enthalpy and heat are similar as long as pressure stays constant. So there'll be some numbers here, typically in kilojoules per mole. Okay. And then what you can do those numbers is you can multiply them. So you could multiply, all this by 2, and then you'd multiply that by 2. Or maybe you're going to take this equation and write it the other way. I'm not saying that with my letters this would be a good idea. I'm just using examples. and then you would negate that. Okay, so hopefully that's familiar. When you see the exact example, don't look at my letters because that makes no sense, but you'll see. Number 5. Number 6. Okay, so sometimes these are in a different chapter. I actually pull these into my enthalpy chapter or thermochemistry chapter, but a lot of times they're in the bonding chapter. So these are going to be the energy change of a reaction is, I always just say BB, which is bonds breaking, minus bonds formed. And so remember that breaking chemical bonds means you have to put in energy to pop them open, okay, to break the bond. And then when you form, when those atoms come together and their nuclei are attracted to each other, you'll energetically get energy back. So just remember that bond breaking is endothermic and bond formation is exothermic. You'll be okay. The last one is called the Born-Haber cycle. Now, this is the one that honestly, if we don't get time to go through it, I might just skip it. But honestly, I like that this cycle includes ionization energy, sublimation energy, electron affinity, bond energies, and lattice energy, and then heat of formation. So I'm just going to kind of draw the arrows because maybe you'll see it. Oh, we have somebody who says hi. I'm going to say hi. I am starting a little early just because I wanted to list these before my students even got here. I'll probably play some music in a little bit just to chill out while we get everybody here. So I'll just say hello. And it's Angela. Wait, Angelina. Hope I can spell it right. Glad you're here. Glad you're studying. It's not the night before, so this is good. I wouldn't recommend studying the night before. I'm going to run another live session, but I don't think I can run it tomorrow night. So unfortunately, it will be the night before. And if I run that one, it'll be on kinetics. So waving at you, hi. So let me go through this one. I'll draw kind of arrows. That's how you'd see it in your book. So what you'll see is you'll usually see like arrows going up like this. And typically there's like 3 arrows going up, and then there's like 1 arrow going down, and then a really big one going down. And then typically between here and here is the enthalpy of formation. And then it's usually an ionic compound. So what are each stages? So here we go. So each stage would be, this would be like the heat of, I always call it heat of sublimation. So it would be taking an element that's not a gas and turning it into a gas. On the IB chemistry test, that's a mess. Oh, well, I'm sorry. On the IB test, I know for chemistry, it's called atomization. So then the next one is going to be the heat of, I guess I'm going to call it ionization energy. So that's going to be the energy. Come on in, Nathan. Got some students arriving finally. That's the energy of removing an electron from a gaseous atom. You'll have the bond energy. So that's the energy. Oh, Richmond's here too. That's the energy to break open a bond. Oh, I undid my computer here. So that's energy to break, usually diatomic molecules, the energy to break that bond. That's always endothermic. And then typically, this is this energy here is the energy, or the enthalpy of electron affinity. I spelled terrible. But that, let me move over here. That's the electron affinity. Usually that's exothermic. Oh, I got somebody else. We have a Carol, by the way. Dane is here, and Nathan's here. I think they got done with tennis. Dane got done with tennis. Nathan?
Oh, that's not here.
He might have been working. We'll say working.
Sure.
Yeah, working. Josh is here again. God, we all are going to like, people are going to like love Josh, like Josh from another school. We won't say what school though, because we don't want people to figure that out. So that was electron affinity. That is usually exothermic, but it doesn't always have to be. And then this big jump here, from here down, is the energy of lattice energy. Now, in some books, lattice energy is typically listed as an endothermic. So then you'd have to negate the sign and make this. Oh, yeah. Carol says, this is no joke, Josh. You should really go on YouTube. Carol, whoever Carol is, says, yes, Josh. Maybe I'll have to show you Josh. We'll have to see if it's okay. Josh is going to become a celebrity. So I'll say, hello. We actually have people from, I should be capitalized, Carol. Hang on, Carol. I'm really slow at this. This is new to me. I'm an old lady. This digital world. It's very confusing. There's Carol. So we have some more people. Abby's here and Olivia. They don't want you to come. They probably don't want to come in front. I'm going to make them say something so that you do not think I'm talking to myself. So Nathan, can you say hi?
Hi.
There we go. Okay, here's Dane.
Hello.
He just says hello. Richmond? He just waved. There we go. Josh?
Hi.
There's Josh. Olivia, she's way in the back, kind of. There, hi. And then Abby is really quiet. I'll be curious if you can hear Abby.
Hi.
Hi, there's Abby. Okay, so honest to God, these are phenomenal students. And I'm so glad they're here because I make a lot of mistakes. So I have, like I said, I'm going to go through these. But the last step is this enthalpy of formation, which if it's an ionic compound, should be exothermic. Okay. So the goal here is I've got 10 minutes. That's why I'm covered this early. So I'm sorry if I started a little early, but I knew how long this is going to take. I'm going to give myself, let me get out of the way here. I'm going to give myself, I wish I had like a kitchen timer. I'm going to give myself 10 minutes on each of these. And if we go for more than 10 minutes, I might not get to the Born-Haber cycle. So that's something that is really low likely on the AP test. But I do like that it ties in all those periodic trends that Josh needs to be aware of. And it's good for you to understand ionic bonding, okay? All right, so we're here. This is it. I don't know if we're going to get more, but we're good. This is a pretty lean group. As you can tell, we are here at 7 o'clock at night. Oh, my own child, don't get rid of that. I'm not trying to promote that credit union. My own child's calling me here, so let's see what he has to say. I'm not joking. Eric, just so you're aware, I'm taping right now, live.
Okay.
Okay, so right now, you're kind of on YouTube.
Okay.
What do you need?
Nothing.
Okay.
Just wondering where you were.
Well, you can log into my YouTube channel and say hi, okay?
Okay.
Okay. I have 3 kids, so I'm a busy person. I'm going to say bye to my child. Bye, Eric.
Bye.
Okay, bye. Okay, here we go. So I'm just going to quick say hello to some music here for a second. Let's get something. I got to erase this. And I remember last time you were stuck watching me erase the board. So my goal here is to not have you just like marinate me in watching this. Let me figure out what I'm doing here. I'm old. I'm so old. Dane, this is taking me forever. I had this all ready to go. Here we go. No, I'm not going to say how I know this person. We're just going to play some nice music. We won't say where it's from. I hope you can hear that. I don't want you to see it because I'll get in. I have a child that might get mad at me. So I'm just going to play that really loud. I have no idea how. There we go. I'm going to erase this now. Oh, I'm gonna turn this down now. Holy cow, that's loud. Oh, Olivia's here. No, Olivia, not Olivia. I'm losing my mind. Kylie is here. So Kylie's gonna say hi loud, and I'm gonna turn this music down. Kylie and I think have the same sickness of coughing. So if I start coughing, Kylie, I don't know if you can hear the coughing.
Hi.
There we go. I think her and I have the same thing. We run a chemistry club. I'm going to blame her for getting me sick. Here we go. So let's get started. I'm going to show you the questions. I'm going to show my students the questions. They don't get a lot of time either, so you guys are all on the clock. Will this video stay? I need this for my final. Please say yes. Yes. Hennessy. Oh my gosh, I don't know who Hennessy is. This is good for Kylie because she's coughing. Okay, so I'm going to show you the problems. These guys are going to have to be quick on their feet because I did not show them these. Here we go. I won't tell you which one's which, but it's one of each 6. Okay, so here we go. So here's the green one. So I'll read it kind of calmly. So we have a coffee cup calorimeter that initially has 125 grams of water at 24.2. Potassium bromide is also at that same temperature, 24.2. Got it, Nathan? I like how Nathan's always in it to win it. I love it. It says then the water it dissolves and the water after goes to 21.1. Okay, so the temperature goes down. If you put in 10.5 grams, what is the enthalpy of hydration, or actually I wouldn't say hydration, of solution or dissolution, okay? We're going to do that in joules per gram and kilojoules per mole. Okay, I'm going to turn off this music here, make sure we don't go to another one. Maybe we'll play music in a little bit. All right, so we're going to use 4.18 joules per gram per Celsius as the heat capacity of the solution. Okay, so that's our first one. So I'll show it again, but my students are kind of feverishly writing some stuff down for that one. All right, I won't tell you which one of the 6 it is. It's a secret, okay? Ooh, I can get my face on here and this. This is fantastic. Okay, so if you're watching this live, I guess you can't pause it right now, but you could pause it later. So I'm going to go on to the next one. So you kind of pick, like, what do you think the green one is of all the 6? All right, here we go. Oh, Hennessy says, thank you. You saved my life. Aw, that's nice, Nathan, huh? Yeah, okay. All right. So there's 1, 2, 3, 4, 5. This is pretty good. It's 7 o'clock at night on a Monday. There's a lot of IB and AP tests, right? Or is IB not yet, Nathan? You would know.
Seniors, IB.
For seniors, IB is even happening right now? Yeah, this is a serious time of year. Okay, here we go. Then we've got the pink one. So the pink one says that we have lithium iodide solid and has a heat, I'm trying to read these backwards, heat of formation that we're trying to find. Oh, Sam's here. I don't know if, I think Sam's been here. I can't read this one upside down. Negative 272 kilojoules, and then it gives us the lattice energy. It gives us the ionization energy. Ding, ding, ding. You might know which one this one is. It gives us the bond energy, the electron affinity, and we know the total lattice energy. But we're trying to find what's called the heat of sublimation. So we're trying to find, hint, hint, maybe one of many steps. Okay, so there's that one. All righty, so that's the pink one. We'll call that with a pink one. So which one do you think that is of the 6? My students should have, and I know that Abby, maybe she'll find it. Abby has a really cool foldable that she made, her notes that she's taken for thermochemistry. She's kind of looking at me. Do you have that along, Abby? She's got it at home. Does anybody have something? Okay, Kylie does. So maybe I'll kind of show you what my students hopefully made when they started thermochemistry or ended it, okay? All right, then we got the blue one. I got to get going because we have 10 minutes for each. This one is the one where I tried to tie in some thermodynamics, okay? So we got an overall reaction. It's a common hot pack. You might use at your, at your house or something when you go to for us, it would be going probably to a football game or cross-country meet or who knows what. So we're going to try to figure out how much heat is released when we have 1 gram of the iron react. Then I'm going to ask you about the entropy. And then finally, I'm going to ask you about the Gibbs free energy with that one. Okay? So try to think about which one that is. And that's the blue one. Then we have the orange one. Look at what that one has. So this one has bond energies. Ding, ding, ding. You might know which one you're going to use. You've got an equation, and it's got a chart. Now, don't judge my chart. But it's got a chart of a bunch of different bond energies to break the certain bonds. Okay? Dane's kind of checking them out. And I'll probably have my students tell me which of the 6 they think it is. So there's a purple one. All we know is the enthalpies of each step. And we have this overall reaction that we want. Okay? And last but not least, keep going. We have a yellow one. Well, we're trying to find, I have it upside, I thought I had it upside down. That we're trying to find the heat of formation of, it would be called chlorine trifluoride. And then I even left a little box here about elements. All elements have what kind of heat of formation? I actually left it blank to try to review. All right, so here we go. Let's see if we can get these done in 10 minutes each. Now we have less time now. So hopefully by around 8, we're done. Okay, let's see what one they think they know. So I'm just gonna kind of hold them up. They got yellow, purple. I'll let them pick which one they want to do first. We got the orange one. We got the blue one. And we've got pink. Hint, hint, I'd wait for last to do that one. And then we've got the green one. All right, what do you guys think? Which one do you want?
I like the color orange.
The orange. Let's do the orange first. Here we go. So we're doing this one first, okay? So when I listed those types, what type is this and how are we going to solve it? So if this shows up on May 9th, right? Thursday. What are we going to do when you see this? Okay, so which one of the 6 types is it? What do you guys think? Callie knows?
Bonds breaking, bonds formed.
Yeah, it's bonds breaking and bonds formed. So here we go. Let's just do it. So let me show the numbers. I'll try to show them one more time to everybody. I'm going to kind of hold them like this. I don't know. Can you guys see these? Oh, or you could be watching it kind of like live while we're doing it live. That's kind of fun. Okay, here we go. So we've got basically, it's called acetylene or ethine, oxygen, carbon dioxide, and water. So I'm going to write it on the board. Here we go. So we're going to take C2H2 gas, and we're going to react it with 5/2 oxygen gas. You can have fractions, people. You can have fractions in an equation. I have students who come back from college saying that professors say you can't. You can. Okay, you can. Okay, 2 CO2 and plus 1 water. So I'm going to put a 1. And then that says a gas. Okay, so here's what you need to do. Before you even use that table, you have to do at least a little bit of dot structures, Josh. Here we go. This is down the path that he was less traveled, okay? So the first thing you have to do is have to say to yourself, this carbon is attached to this carbon, and then there's a hydrogen on each end. This means it's like a dual center, okay? And if we really quickly go through electron pairs, you're going to have, let me count them out here quick. You're gonna have 5 pairs, okay? So there's 10 electrons in this dot structure, 5 pairs. And so if you place the first ones, like you normally would, like that, okay, just to bond them all, you do not have a lot of pairs left, and the hydrogen is okay with the duet rule, but the carbon is not. So you need to have a triple bond there so that each carbon has 8 electrons. Why that's important is because on this chart, I try to fool you. There's carbon single bond, double bond, and triple bond. We need the triple bond, okay? So we need this 839. So to break this right here, we're just gonna put a little note. This takes 839 kilojoules per mole. Then, I'm gonna show you the chart again. To break the carbon-hydrogen bond, it's 413 right there, okay? I'm just gonna list them kind of this way. I won't put the units anymore. And then you have to kind of remember, if you don't, you just gotta, do it yourself. Oxygen's gonna have a double bond. So on this chart, I did 2 things. I kind of showed you a single bond and a double bond. We need the double bond, so that's 495. But we gotta be careful. We're gonna multiply that by 5/2, okay? So we do need the 5/2 in there when we do the math. And then this right here is carbon dioxide, so a little arrow. So that is, these dots nicer, there we go. That is 2 double bonds for the carbon dioxide. That's another common one where students will mess up. And then there's a 2 in front of that, so be careful. Now, for a lot of times with the carbon dioxide, I'm not sure why, but let's just go with it. It's a higher energy to break that bond, so it's 799. And that's for each. And that's kilojoules per mole. And then that's going to be multiplied by 2 moles. Last but not least, we have water. Let's even draw that one the way it looks, which will be bent. Okay, 104 for this angle or less than 109. And then that energy, and you have 2 of those, okay? Those are on the chart. If you had a chart in your book, it would look a lot nicer than mine. So those are 467. Okay, so what you need to do is say that the total energy of this whole reaction is going to be all the bonds broken. So don't worry about it with this one. Let's just break them all, okay? I know sometimes you can keep some, but I'm just going to break all the bonds in this case, okay? So we're going to have 839 kilojoules per mole. And what you could do is you could multiply that by 1 mole of that, okay? And then we're going to have 2 of the 413s. Okay, and those are all the, no, not quite yet. We have to break 5 halves of the 495. Okay, so I'm trying to write really big because sometimes when I watch these back, I realize if I don't write really big with just the computer here, you don't see. So we have all of those are the bonds being broken. Then we're going to subtract that from all the bonds being formed. So we got to be careful. There's actually going to be 2 for each, and then there's 2 moles of it. So I'm just going to say there's 4 of them. Let's see what Dane says here. All right. And then the good news is there's just 2 of the 467. All right. So what you guys want to do, ooh, that should be a closed bracket. I have the answer already on the back and really prepared this time, so I know we got to move fast this time, getting close to May 9th. So on the back, I have the answer. So beep, there's the answer on the back. So let's see if we get it. In front of my students is fast enough. Did we get the right answer? Nobody did it. Josh is feverishly punching, so he's got one of these. Now on the AP test, this would probably let me get over here. This would probably have to be, let's see, made the numbers really easy. So it'd probably have to be an FRQ. I've seen this more on the FRQ than anything. So hopefully we get the number that we have on the back of this piece of paper. And like Callie said, she went orange. Okay. Yep.
Negative 1,227.5.
Yeah. Okay. So let's do the real answer, Kylie, from the calculator. 1227.5. And then typically the moles goes away because really we should have multiplied each one of those by moles. But we have the sig figs wrong because this is one of the few times when we're adding and subtracting, we only keep the same number of decimal places as the one with the least. No, none of these have a decimal place. So that means we have to round this to no decimal places. So what would that be?
Negative 1,000.
Yeah. Box it out. I'm telling you, people who grade the AP exams love it if you box it out, have a label, have the sign, okay? I'm telling you, the sign is been the nemesis of many students. You need the sign on there. So make sure you got a negative sign besides that, okay? So, and this makes sense, it's exothermic, it's combustion of a hydrocarbon, okay? Okay, we did it. I think that was under 10 minutes for the first one. So that's 1 of the 5 is done. So the bonds breaking minus bonds formed is done. I'm just gonna check with my students, how we doing? Okay, they're all kind of shaking their head. Yes, I'm gonna maybe even have Olivia or Abby shut the door because there are some people who help kind of clean, tidy, the building when usually we're not here. 7 o'clock at night. Okay. We may just want to just pick a color. I'm kind of saying like purple. Kylie's in charge. I like this. Kylie, I like you. I like that she's in charge. Okay, so we've got this one. Are you ready, Josh?
Yep.
Okay, this one I think he's familiar with. Okay, so this one we've got 3 equations. Let me see if I can even hold it a little higher here so that my students can see it. So you have 3 equations. We got a final equation that we're going for, and then we basically just want to find the total enthalpy. What does it sound like? Hess's law, okay? Hess's law where you have traditionally just the, where you flip and multiply, okay? Not the summation equation. Okay, here's the deal. I have to erase the board again, so I'm hoping I can play music because nobody wants to watch me erase a board. So here we go. We'll play this one now. I don't know if it'll play. Come on. There we go. Oh. Okay, here we go. Because at least you can just chill out for a second. I wish I could put this on. I don't know what that looks like. That looks terrible. That's not a good idea. Dan says, put it right there. You can't see that thing. Here we go. Okay, here we go. So here's the equation. I'm going to write the 3 equations on the board. So you have nitrogen. I'll just tell my students. They should be able to write this. AP test writers are now kind of nice. I'm not. Nitrogen monoxide, ozone, producing nitrogen dioxide and diatomic oxygen. That's the first equation. I'll tell you the enthalpy in a second. Second equation has ozone and then 3/2 of diatomic oxygen. So it's kind of a decomp, okay? Then we have oxygen turning into elemental oxygen. I mean, that's possible. So instead of diatomic, it's elemental. Okay, so those are our 3 equations. All right. The goal here is to get to here. Okay, so this is our goal. Nitrogen monoxide gas, oxygen as an element, and then nitrogen dioxide. So I'll be honest, it's kind of a weird reaction, but we can still do it. Okay. I always tell my students, don't get worried. A lot of times when they write the AP exam, they kind of come up with something, I'll say creative. Okay. So you never know. Okay. So I'm going to write the first one. So you have nitrogen monoxide gas reacting with ozone, turning into nitrogen dioxide gas and oxygen gas. And the enthalpy of that change is negative 198.9 kilojoules. Okay, so it's exothermic. Okay, next one. We have ozone. Kind of a fun dot structure to do, but we won't do it. 3/2 oxygen. And then we have negative 142.3 kilojoules. Let me see if I'm writing big enough. Yeah, that's definitely viewable. Okay. So then we have oxygen turning into just elemental oxygen. So it's very unique. Okay, and then we have that being 495.0. Which really you can almost consider that like a bond breaking kind of energy. Okay, so what are we going to do? So these are not heat of formations, so we don't use that summation equation because none of these are really forming an element or forming a compound from its individual elements. So we have to pick them. We have to flip them, multiply them. So what are we going to do? So I tell my students, what do we want to leave alone? Okay, Kylie's got some ideas.
I'm going to keep the first one, flip this, like, don't want to flip it.
Yeah, don't do anything to that first one for now, right? Okay, what do we want to do the second one? Yeah, this is we're going to have to flip. So I'm just going to quick kind of just do that. So we're going to have 3/2 O2 here. And then ozone here, right, you guys? This is where I'm glad I have some students here to check me. Is that right? Yeah, right? And then we got to go over here and make this positive, okay? Now, when you're doing thermochemistry, this is all hunky-dory. But my students know that when we get to electrochemistry, and these are half cells, what should we not do to the cell potential or the voltage? Never multiply it, okay? So be careful. With enthalpies you do, voltages you don't, okay? You just still flip them, but you don't flip the charge or flip the number sign, number positive, negative, and then you don't multiply them either. Okay, what about the last one? This one's the toughest. This is the toughest one.
Was it multiplied by 1/2?
Yeah, Dane's got it. Okay, so we're gonna move this, so flip it. This is the toughest one. And then we're gonna put O2 on this side as a gas. So it's gonna make this negative. Okay, so we flip that. And then Dane noticed that we need to have half of that. Okay, and that's okay. A lot of times you'll multiply these reactions, but in this case, you would divide it. It's the easiest way to go about it. So that means you'd multiply this by 1/2. So I'll just show you, okay? You do that first, okay? Then you would just turn this, bless you, you turn this into just a 1. All right, let's forget it. And then this would be 1/2, all right? And then this would be divided by 2. Okay, so make sure you get that in the end. Now, the goal here is that when you get to the end here, we'll just kind of add up what we kind of all accumulated, almost like a bank account. You just add them all up and see what what you have or what you owe, right, Nathan? Come out ahead, I hope. And then we'll check the other equations. And this is where you could tie in kinetics at this point with intermediates. I don't think we have a catalyst here, but we do have a couple intermediates. So maybe look up that. How would you pick out which ones are the intermediates? Okay, so ozone's going to go away. All right. Now, this is where things can get kind of a little tricky, right? So let me just do this. This is like 2 over 2. And so if you do 1/2 and then 2 over 2, that's 3 over 2. Oh, fractions are your friend. I always tell my students, fractions are your friend. Okay? So that's 3/2, so those will cancel. So you get this one and this one together gets rid of that one. And you carry down what's left just to kind of double check. And we have it, okay? So then what you want to do now is just figure out the math there. I have the answer on the back. So hopefully they'll tell me the right answer that I have on the back, okay? And this is kind of a reaction where if you were a young chemist like these guys are, and probably you are, you don't have a lot of instinct with this one. It's not combustion. It's different, you know, so they take away your senses, which would be a good AP question because you're totally going blind with just what your numbers tell you. So what did we get? Anybody get an answer? Somebody here could type it, right, Dane? Nobody's typing it though. Kylie's on fire tonight. Kylie? What'd you say? Olivia. Okay, we'll let Olivia take it here. Yeah. So delta H goes negative 304.1. Whoops. Kilojoules. Add that in there. Save it. And then, box it out. Don't forget your unit. One fast way to lose your point on the AP exam is by not putting a unit. Don't be that person. Or people. Lots of people. So put a unit. Don't forget the negative. This is exothermic. Kind of different than probably what you thought. We're doing really well. Okay, so we are about 2 done, under 10 minutes each. So we're fast. Ooh, there's the answer. Okay, so there's that one. All right, what do we have left? I'll try to find another song here. I don't know if you like the songs, but I'm just going to keep playing them anyway. Here we go. Let's try this one. We're going to go to the next one. What do we have left? I'm going to skip the pink. Here's some more music while I erase the board. So we have green, blue, and yellow. Dane says green. Let's do it. Okay, so here's the green one. I'm just going to set it on the board. I don't know where else to set it. Because this just covers up the camera. Dane was like, what are you doing? Covering up the camera. Here we go. Calorimetry. You should be like finding an equation, thinking about how it's going to be exothermic, endothermic. Is the water gaining heat, losing heat? All that stuff should be going through your head right now. What numbers to use. Here we go. Here, I'll crank this up a little bit. Kylie can't hear it in the back. Oh, she can hear it. I'm not very good at this. I need like a Vanna to kind of hold the question. Okay, here we go. Gotta get rid of that. Things tell me to double click to pay. I don't want to pay for anything right now. Here we go. So we got a coffee cup calorimeter. Ding, ding, ding. 125 grams of water. It's going to go from 24.2 to 21.1. And then we got 10.5 grams of potassium bromide. When do you use that? Think about it. Telling my students even right now. When do you really use the 10.5? And how? Because there's actually 2 answers to that. And then here's what the heat capacity they're going to say the solution is. And we want it in joules per gram and kilojoules per mole. Here we go. This is a bigger one. This might take us more than 10 minutes. Here we see. Okay, so whether you like it or not, you don't have to draw a picture on the AP exam, but we're still studying. So I would draw a picture, okay? Don't be a hero right now, but on the AP exam, don't draw this picture, okay? So here we go. We've got a thermometer that's going to go from 24.2 degrees to 21.1 degrees. So that's our delta T, okay? We have 125 grams of water in here, but we're putting in 10.5 grams of potassium bromide, okay? All right, we know that the heat capacity, so I can help with delta T. We know we want to use Q equals S or C, mass, and delta T. But we also know that the heat capacity they're telling us of the whole solution is 4.18 joules per gram per Celsius. Now, here's what I need you to do before you do anything else, okay? Yes, 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 we're going to put numbers there, okay? Everybody kind of knows that. The problem that people will make is they don't realize that this solution dissolution, I'm going to say that. So this right here, this potassium bromide, solid, dissociating into potassium ions and bromide ions. Do this right away for yourself. Let's see if you have room here. I want you to put right over here the heat of solution. Is it negative or positive? Just tell yourself right away. If the temperature of the water is going down, that means the water has lost heat, okay? So who's taking the heat? The dissolution process, right? The KBR, okay? So the KBR sort of dissolving, becoming ions, or you can say that the enthalpy or the heat of dissolving is taking it. So this right here needs to be a plus. That's where you'll make a mistake, okay, for this one. Now, if the water's temperature went up, different story, then it's exothermic, okay, but the water's temperature went down. So let's keep going. What is the delta T? And if we're going to base this on the water, we can. Okay, we can do that. But be careful. I'd actually even say that it's the whole solution. Okay, what are we going to put for mass? That's the other trick thing here. What do you think? It's basically 125 or 125 plus the 10.5. What do you think? Abby's kind of saying together, right? Okay. The biggest thing I found is students say, well, when do I add it? When do I not? Okay, if you stick a metal in there, not an alkaline earth metal, something like copper, okay? The copper is not going to dissolve in the water. It's not going to add to the solution, okay? This is going to dissolve, so you add the mass in. If it was a metal, the metal will just sit there. So then they exchange the heat in a way that the metal's not dissolved into the solution, okay? So this time you add them. And then what about right here? We can make it negative. It's fine, because this is supposed to be T final minus T initial, right? So what would we put? What do you guys think? What's our delta T? Let's not put the numbers in. Let's just solve it. Yeah, negative 3.1, right? Are we good with that?
Mm-hmm.
Okay, so let's just switch this out. We'll be faster today. So what is our heat it's really what I'm going to change it back, kind of the water solution or the aqueous solution, and it's going to be negative. It's okay. Like this number right here, or you can get rid of it here, it is going to be a negative number, but that's okay. That's what the water is losing. And then the solution, dissolution, that's what it is taking. What do we get? So the grams are going to cancel kind of here, okay? Celsius is good. We don't have to turn it into Kelvin for this thing. So what did you guys get?
Negative 1,755.813.
Okay, so negative 1,7. It's different than what I have for an answer. What's a check?
Oh,
That's okay. I think that we're right though.
I got negative 1,755.
Oh, okay, 1,700 and for sake of purposes here. Or 170 or 1,000?
1,000.
You got 1,000 also?
Yeah.
I wonder if there's an answer. The back of the book might be wrong. If we all have it right, I'm going to go with it. So what'd you, so 1,700 and 55? Or 5.5? Or is this?
Yeah, 1755.
Okay, but then 6 figs. Okay, so then this is going to be in joules. Are we okay with that? Oh no, I think we're fine. We're fine. I know what the dealio is here. So let's just leave that for a second because we always have to do what the, I always say do what the AP test wants you to do. So the first answer they wanted was kind of not a delta H, but I'm just going to say it sort of is. They wanted it per gram. And then another one they wanted, which is the normal one. This is the one I would suspect you're going to need on the AP exam, per mole. Okay, so let's just do both. Okay, the gram one's easier. So how are we going to turn that joules into joules per 1 gram? And then be careful, the heat of the whole solution is actually plus 1755.81 joules. And we're going to divide it by, anybody know? This shows up a lot. Okay, so what does that turn into? And then now we probably should do sig fig. So honestly, it looks like, with our difference in temperature here, it would be just 2 sig figs as a final answer right here. And so this is our first final answer in joules per 1 gram. Right now we have 10 grams. So this is going to bring it down by 10-fold, okay, approximately. Okay, so what do we get? I know what this has. I'm hoping we get it. And it's plus, okay, I'm going to add that sign right away because this is the dissolving of the potassium bromide is endothermic. We have it. We're doing okay though. I'm kind of really watching the time today. We're doing about 10 minutes for each. So that's impressive. And on the AP test, what will happen is if this is a multiple choice, they'll make these numbers a lot easier. They a lot of times like to make that just 4.2 because then you're just multiplying by an easier number. And then a lot of times these other numbers will be just 3s or like 200 or something simple, okay? What do we get?
167.22.
Yeah, so I'm gonna write that up here. You got 167 point something, but again with 2 sig figs, we got to round that all the way to just 170. Okay, we're there. Okay, I won't show you the second answer, but there I have the one answer. Okay, we got to keep going. So we got this one done. Now, how are we going to get this answer in kilojoules per mole? Again, put the positive sign because that's not going to change. But how do you get it in kilojoules per mole? So we kind of have to have I always say like a little detour right here. We know it's plus 1755.81 joules. So let's quickly just do this fast because we're AP Chem. What's that in kilojoules? Yeah, right, 1.75581. I mean, we're carrying a lot of digits here, okay? Still positive, still endothermic. And how do we divide it by moles? I'm going to kind of sneak way up here. Carly, you're going to make it, girl. I stopped coughing finally today. It took a long time, though.
It's been a week.
I know. We're just going to, I think after the AP test, we're just going to have, like when you're little kids and you bring your sleep mat or something. Just Dane's going to be like, I'm not doing that. But just read and have a book and just maybe a little snooze. Right, Sam? It sounds great. Those little nap mats that they sell for pre-K. I don't know. We should just do that. Little camp mat. Okay, so what are we going to do? KBR, what's the molar mass? Periodic table, right? I don't know these two. Is potassium 39? A periodic table over here. And you can't do this on the AP exam, but my students are they'll just literally, they'll be like,
Yeah.
Siri, what's the molar mass of potassium bromide? I mean, that's what they'll do.
Here's what I found.
See? She won't read it to me, but sometimes she reads it to me. Okay, what did we get? Nobody has it? It's going to take us a little more. We're past 10 minutes now.
Should be 20 kilojoules per mole.
Okay, So he has Dane's already like, we're done. He has 20. How many sig figs, Dane? We can use.
It's only the 2. So
Oh, this is a tricky one, isn't it, Dane? What did you get for the moles here, just to help everybody else out here?
I actually just did it all.
Oh, Dane was
39
fast.
79.
Okay. Nobody has a molar
Oh,
mass?
that's 80, so-
He's right. It's 20. This is the tricky answer. It's 20. I always tell students with the special dot. The special dot that says the 0 is significant, meaning it's exactly 20 as best as we can measure it. So I'm going to, hang on, I'll be right back. What is potassium? 30. I was right, 39. Yeah. And then bromide is 80. So it's like 119. Okay, so then we're going to take 10.5 divided by 119. This is a step that students mess up on the AP exam. I'm telling you right now. You take a kilojoules and you divide it by a moles, and you get kilojoules per 1 mole. Get it right. It's surprisingly wrong. My students they're to blame too. They do the same thing. 0.088 is what I have. And then what Dane did was he took this number and he divided it by 0.08. That's an 8, I promise. Per mole. Oh no, that was right. This was supposed to be a 0. And I tell my students in first year chem repeatedly, why do we never use a mole amount? Like in our realm of high school chemistry or higher even, a mole amount is a lot. Okay, so we use small amounts, small mole amounts. So this is a decimal. So when you divide these two, Dane, what did the calculator give you that you?
It was 19. Hold on. 19.728, but there might be some compounding error.
Yeah. Okay. So we have that per 1 mole. Still positive though. And see what happens is you round that up, but you want to keep it. Now, I'm not promoting this at all. Okay, please don't think I'm promoting this. This is ridiculous talk. And I would put the per 1, make sure the positive's there, circle it, okay? Now that's kind of crazy. And you could put per mole of KBr. I mean, you could get really picky about the labeling. But I have seen students do 2.0 times 10 to the 1. Okay, it's a good way to put the sig figs. Okay, we used about 3 more minutes than we were supposed to for that one, so let's keep going. Okay, we are done. Okay, so green's done. What leaves us with, is this really it? Purple? No, we did purple. We did orange. We did green. Uh-oh, who are we hiding from? These two. And I'm pulling out pink for now. So do we want to do this one? We'll tie in a little thermo. Or do we want to go for this one where we find the missing enthalpy of formation for chlorine trifluoride? Yellow is the win. Then we're going to do this one next, okay? I don't know if I play song again. This is ridiculous, but I feel like nobody wants me to watch. If you're doing a normal video, you would cut this part out. My phone's got to stop locking. Maybe I should have them play music. Here we go. We'll just keep playing the same one here. Okay, here we go. We're going to do this yellow one, though. Nowhere to put it. All right, here we go. Here we go. So here it is. This yellow one. We are going to do this one. Now, this is the one that most students want to see. However, I gave it to you in a kind of a challenging option. So we are actually trying to find, like it's in the table in the back, we're trying to find the heat of formation of chlorine trifluoride, and it's not there, okay? Now, for my students, we have used the National Math and Science Initiative documents. So I think that her name is Renee McCormick, and she calls this, isn't she calls Big Mama verse 2, I think. So here's the equation that you're going to want. You're going to want that you know that the reaction's entire energy total is the summation, see if I can do a summation sign, of the moles of the products times the heat of formation of each product at standard conditions. And I went through in the beginning of this video what the standard is. I'm not doing that again. And then minus, my voice is actually going again, moles of reactant times the heat of formation of each reactant at standard conditions. Now, just because we're running kind of long, I'm not sure if we'll do it, but realize that in the places of those H's, can be G's, which are Gibbs free energies. Same similar equation. The other thing that can be in place of those H's, almost, is an entropy, which is an S. They're all the same kind of equation. You'd use an index, or you'd need somebody to give you a table. Okay, so kind of watch for one of those. They're not the most challenging. They're actually pretty easy money. So here we go. So I'll just list the numbers that I gave you. Okay, so here's the reaction. 2 chlorine trifluorides as a gas are going to collide with 2 moles of ammonia gas particles, and they're going to produce nitrogen gas, hydrofluoric acid, sort of, or hydrogen fluoride gas, 6 moles of that, and chlorine gas. And we're trying to find the enthalpy of this reaction, and it'll be in kilojoules per mole, okay? But we know it this time. So this time we actually do know that number, which is why this is a little bit different. So actually we do know this number, and they said that it's negative 1196. I don't know if you can still see it or not. Let me look here. Barely. Kilojoules, okay? So that's why this one's different, and look for these, that you actually know the total this time. You're not trying to find it, okay? So that means in this equation, I know that it's negative 1196 kilojoules on this side, okay? I know that already. A lot of times in the first time you learn this problem, that's what you're solving for. Okay, so I'm just going to list some things here. This one, the heat of formation of that was 46 kilojoules per mole. HF was negative 271 kilojoules per mole. And then we didn't know this one. And then, how dare they? They didn't tell us the other ones. But why do we not care? What should I put in this little box right here? What do you know? Richmond, you're the best. 0. Now, I was talking to one of my AP students today, and this is worth it. So a little shout out to, I call him, I won't say his real name. I'll actually just say Spencer. Everybody knows who he is. It's not really his name. But him and I were talking about, when does a thermodynamic function equal 0? And it gets to be a big talk. Like, when is entropy 0? What's the answer? Like, when is entropy 0? There's only one answer to this, people.
A perfect crystal at 0 Kelvin.
Yeah, perfect crystal 0 Kelvin. That's never going to happen. Okay, so everything has entropy. Next, how about a heat of formation of some kind of element? 0, okay? The rest of them, everything else has a compound, Nathan. It's got some kind of energy, okay? How about delta G? When can delta G be 0? Lots of answers here. 2 for sure. Anybody know? Equilibrium. I heard it. Nobody said it. I heard it in my head. And what else? Change of state, melting, boiling. Or, we'll try to show you before the time's done, if you want to solve for the temperature that made something be spontaneous, you can put in a 0 just so you can find the temperature, but you got to be careful. You need to say higher or lower depending on what the delta H and delta S is. Abby's going, yes, okay, it's tricky, but you can put a 0 there just to help you solve it, okay? Maybe we'll have time for that, I hope we do. But let's do this one. This one's actually, I think, easier. This yellow one's kind of the winner for the easy. Me and my students are already done. Here we go. So then we got to put products, okay? So it's 1 time, I'll put it in there, okay? So it's 1 mole times 0 kilojoules per mole. This is silly, I don't know why I'm doing this, but I'm gonna do it anyway. That's for the nitrogen, but just in case you don't understand, let's put this in brackets. Plus 6 times moles times negative 271 kilojoules per mole. And that's for the HF. Plus 1 mole of chlorine. Just in case you didn't understand what Richmond was kind of throwing out there for you, right, Richmond? Let's just make sure everybody's super clear. Times 0, because it's a pure element. It doesn't have a heat of formation. Then we got to subtract that from, those are our products. Be careful, these are our products, from the reactants. Well, we don't know this one, so it's 2 times, let's just put, I like question mark. A lot of students will say put an X or a Y. I don't want to, okay? Let's just leave it as question mark. And then plus 2 times negative 46 kilojoules per mole. And then really I should put 2 moles. Let me slide this over. I can hear the calculators going already. I love that sound. My goal when I retire is to be one of these AP test people that runs the AP test thing. And I really do feel like when I sit in that room and I hear these students that I probably don't even have anymore, when I start to hear this noise, I feel like I'm gonna be like, oh yes, that's the sound of science. I'm trying to get Dane to smile, he's not smiling. Okay, here we go. Oh, I think there's a little smile there. He's a little smirk. Okay, so here we go. What do we get? I don't want to show all the math. Don't make me show all the math. Let's get to the answer. Let's cut to the chase. Or should we show the math? Anybody have what the first big bracket equals?
Negative 1,626.
Negative 1,626 kilojoules. Is that right? Okay, fantastic. And then what is this? I think I can do this, but I don't want to mess it up. So it's going to be plus negative 92. Okay, and then over here we have negative 1196 kilojoules. Okay, so I mean, really, if we were doing this, what would you do? You put this over here, right? Let's just do it. I think we probably are wasting our good time here now. And then this is going to be negative 2 times the question mark. And then what's going to happen to this? It'll be plus 92, isn't it? Oh my goodness, here comes that cough, Golly. So then I'm going to put this on this side, right? So then over here, I'm going to have negative 92. Oh boy, let's hope this gets to the right answer, right? Okay, so let's at least maybe get to here. So negative 2 times this question mark, whatever it is. What does that equal on that side? I'm off the screen. That's okay. You don't need to look at me. What do we got over here? There are 4 people watching. So I don't know if this Carol and Angelina, I love you for still watching, and Hennessy, but these are supposed to be my students watching. Who should we be yelling at? Andrew? Let's just start yelling at names. Who should be watching? Spencer. Eli, right? Emma, Megan. Ashley, let's rat her out, Josh. Ashley, we could keep going. I hope they're watching or they're going to watch later. Maybe they're going to watch later. There is a track meet going outside, isn't there? So then we can't yell at too many. Okay, let's keep going. What do we get? I'm trying to buy some. He's in track. Andrew's running probably right now. Okay, what do we got? Over here?
Oh, let me see that. Oh,
This would be negative.
not negative, positive.
This would be positive. 338.
38.
Just in case we've got some people who are stressed, they're stressed out right now. Then we divide by 2, right, but negative 2. So in the end, what's our question mark? Gosh, I hope it's the answer I have on the back of the yellow paper right there.
Negative 169.
Yay. Okay, kilojoules. And then it is going to be per 1 mole because we did account for this too. So if you really want to be really picky, this was 2 moles, and then we divided it. So this is per mole, and you could be really thorough here, of the ClF3. I mean, and you could even say per 1 mole of that. So that's how many kilojoules per 1 mole. So I'm going to do this really quickly, though, so you understand what you just solved for. Because a lot of students will hey, solve for it, yay! Okay, but here's what you really solve for, because I try to get my students to think about what they're really doing. This number, this is what that number means. If I was to take, what elements? Chlorine, gas. And I was to react it with fluorine, gas. Dane is already like, yes, let's do this. I don't want to do this. It sounds scary. And we're going to make, what are we going to make? ClF3 gas, okay? We want this to be a 1, okay? That number is the energy it takes to make 1 mole of that. So what kind of fractions are going to be sitting over here if you're doing a heat of formation? Are we okay with that? And then, how do we turn that into a 3? 3 halves, right? Well, I'm looking at Dane. I always have to check. It's almost 8 o'clock at night, so I'm asking Dane to check. That's right, Dane, right? So this is what this means. We took a synthesis or composition reaction, I should say synthesis, composition, or formation reaction, and we solved for the energy that it would have taken at standard conditions to make that molecule from the individual states. Now, we probably shouldn't do this, but I'm going to do it anyway because Josh is here. Josh, let's just do a dot structure for this. Let's just do it, okay? You try it right now, okay? Because really a lot of these videos about me making sure that in how many days, Josh? 3 days?
3.
He goes from no knowledge of any of this to be like, mwah, you know, perfecto. Okay, so Josh, give it a shot. I'm thinking this could be an expanded octet. I'm not sure, but my instinct says it might be. It doesn't have to be, but I'm thinking it could be. Somebody sent a message to me. Did you hear that? Popular today. That was my mom. You know, your mom is always your mom. There's a little piece of advice for all of you. I'm old. That was my mom. I don't know why she's sending me a message, but she's sending me a message. Mother's Day is not till the weekend. Here we go. Let's do it. So Cleo, this might be more than an hour. For those of you who are watching this, you probably say, I don't even care. I just want to get ready for the AP test. Here we go. How many dots are we going to place? Do total dots quickly. 28, right? Somebody just tell me if somebody says something wrong. 14 pairs, right? Which element's going to go in the middle? Don't let them fool you here. It's easy. Cl, right? Right? Okay. And then we've got just fluorine, fluorine, fluorine. So north, south, east, west, just pick it for now. This is not a Vesper structure. We'll try that in a second. Okay, how many, what are we going to do first? How many pairs? 1, 2, 3, right? You're going to dole out 3 pairs quickly, immediately. What about your halogens, the fluorines? They do not expand their octet. Holy molies do not, holy Avogadro moles, okay, do not expand a fluorine's octet. Has to have atomic number of what? 15 or greater, okay? So just do this. 1, 2, 3. So how many pairs have we placed? 6, right? 7, 8, 9, 10, 11, 12, right? How many pairs do we have to place? 14. How many dots you have left? Don't be that person who just doesn't put them. You're going to put these 2. And you're going to do what? 2 more, okay? How many regions of electron density? How many electron domains? What's the electron geometry? I just took a picture of it. 5, okay? What's the original shape? This is a good one. It's okay. We're going to go over an hour. I don't even care. I'll probably get sweaty. To say it, not me. I always tell them, I'm not showing up on May 9th. You are. I should get a 5. Be embarrassing if your AP Chem teacher couldn't get a 5, right? Right, Richmond? You'd predict me as a 5. Or higher. Maybe I'd be that perfect score student. There's like 1 or 2 a year, whoever they are. I don't know how you do it, okay? They've got to make AP Chem like top priority. Like that's got to be the top thing in their life. Okay, it has to be. Because they're almost as good as their teacher at that point. Okay, here we go. What's the original shape? What was that one? Oh, Kylie, you're going to be okay, girl. What's that called? Trigonal bipyramidal. Now, that's not the answer yet, okay? But that's the original electron domain shape. Hybridization? The sp3 or sp3d. Now, I don't think they're going to have any of that on the test anymore, but let's just throw it in there. Where are the lone pairs going to go? I said this on one of the other videos. Where's the biggest bond angle? I think Kylie's right with the T-shaped, actually. You're way ahead of the curve, aren't you? I think. Aren't these 120s here? Okay, so these lone pairs are going to take up the biggest space they can find. And 120 is better than a 90, okay? So then does that turn out to be T-shaped? Yeah, it does. Good job, Kylie. What could you do? Polar, not polar, intermolecular forces, on you go. Okay, let's be done with this now. All right, we're going to keep going. I don't care. Okay, because we do have to finish this one for sure. We'll try to do the pink one if you want to stay. So how are we doing? I'm going to show the blue one quick. How are we doing on the, I don't know if we're going to have music. I'll try. Just kind of stare at that for a second. Josh, how are we doing?
Good.
He's good. Okay, I'm just going to keep playing this. So I got to erase the board. Here we go. That might be a little loud. Okay, there we go. That's good enough. Let's go. Here we go. There it is. There are 2 left, okay? This totally sounds like the Born-Haber cycle. Okay, so but we'll see. If we have time, I'll slap that one in fast, but let's just go to this one. So this one, what's left? Plain old stoichiometry, okay? The good old stoichiometry. So let me write the reaction. So we got 4 moles of iron solid. This is what happens in those little heat packs that I know I take when I go downhill skiing. Or, you know, we are in the greater Green Bay, aren't we? So, you know, there's a lot of Packer game people here that take these and they wear them all over their body. Okay, so these are those hot packs. Very exothermic. It tells us already that. Okay, -1652 kilojoules. Okay, and a lot of times now on the AP test they'll say per mole of RXN. There's a lot of debate on who likes that, who doesn't. I don't care. Okay, just roll with it. I tell my students, roll with whatever it is. What that means is that's the amount of heat if you had 4 moles of iron. That's the amount of heat if you use 3 moles of oxygen. That's the amount of energy or enthalpy or heat, because we're going to keep pressure the same. If we have 2 moles of iron, let's name it, iron 3 oxide, or you want to be fancy, ferric oxide. Okay, so 2 moles of ferric oxide produced, that's what we get. Okay, this is we could say this is a heat of formation. Not really, because it's not per 1 mole. Okay, here we go. We're going to put in 1 gram of this. This is what A says. 1 gram of iron and excess of this. How fantastic. There was a harder problem I could have picked, but I said, no, I don't want to do it. If you're going to put enthalpy in this reaction, you'd actually put it on this side, and then you could just leave it as no negative, but you need to know that it is negative, okay? So I would recommend leaving the negative. It looks kind of weird, but it's fine. Here we go. So you're going to say 1 gram, and I converted to what I call the fence post way to do stoichiometry. I don't know why, but I know the molar mass of iron for some reason. 1 mole of iron. Then you're going to say, for every 4 moles of iron that I react, I'm going to get 2 kilojoules. That's that whole per mole of reaction. You just put the mole amount in there. It's not hard. Don't make it hard, okay? Here we go. Happy face this year. I should smile more because we're getting close to the AP test. What did we get? I have the answer already. So it's actually kind of slick. It's quick. It's quick. So it's a negative. We know that, right? It's got a kilojoules. In fact, I tell my students, before you even put a number in there, box it. Do this. Box it. I just undid my computer. That's okay. Put a negative sign if it needs a negative or a positive. Now put the number, okay? What do we get? Everybody got it? Did you do something with a 7? This is what I get, 7.39. Probably with some sig fig things, but we'll just do 3 sig figs. Why 3 sig figs? Your mass that probably you had an electronic balance that went to 2 decimal places, totally normal. Okay? How are we doing? Good? Easy one. Next one. I added this one in. This was kind of new. Is the entropy increasing, decreasing, or remaining the same? Justify your answer. If you have not answered a question by now, May 7th? No. 6th. May 6th. If you have not justified your answer by now, here's the time, okay? Higher, lower, or the same? So let's just pick it. What do we think? Entropy, higher, lower, or the same? This was A. What do you guys think? So entropy is delta S, change in entropy. You could say positive or negative if you want to, but really I'm just asking for increasing or decreasing, meaning more entropic. That would be the word, or less entropic. You can put a sign. What do you think the sign is? Positive or negative? Uh-oh. Negative I saw. Okay, I heard kind of a negative. What does negative mean? Yeah, less entropic, or if you don't want to say that, you could say more order, right? Now, why? Because. Here's the moneymaker. You need the because. What do you think you're going to say, Kylie?
One is a solid gas going to just a solid, and it's going from 7 moles to 2 moles.
Yeah, lots. I would put it all. Do you hear everything Kylie said? Write that all in a nice sentence. Here's what she said. You make the words make sense, though. She said, you've got solids and gases as reactants. Blah, blah, blah. Turning into, make a sentence out of this, people. Turning into just a solid as a product. So here's where you want to be fancy. You would say something like, solids are more organized than gases. So it's becoming more ordered as it becomes a solid, but there's more than that. And this is really, to me, the big one. 7 moles of reactants are turning into, don't read my writing, into 2 moles of product. Now, some of you have been coached to say microstates, and that's fine. I don't coach my students to say that. They could now if they wanted to. I had a group who we sat out in the hallway and we did some studying with some big whiteboards. And I just said there's only like 10 of you, and depending on how you sat out in the hallway would be all the different microstates. And there's a lot of possibilities if there's 10. Now, if there's only 2 students, well, number one, I don't know why I'd have an AP class with 2 students. But if I only had 2, there's only so many options as to how they could sit. Those are called microstates. So when you have 7 particles or 7 moles, and then you have 2, there's just less microstates. This is microstate. Now, I don't think you need to say that, but if you do, it'll just make you look a little cooler than the average. Okay, let's keep going. If this reaction occurs at room temperature, it's really just rusting. We all know that happens. What is the sign of delta G? And does the enthalpy or the entropy sort of drive this reaction? Okay, let's keep going. What do you think? Let me get rid of the microstates. So if they said it happens, delta G is negative, okay? And then it's because who's sort of in the driver's seat, the enthalpy or the entropy? What do you guys think? Okay, let's just put the equation here. Delta G, I'm going to try to tie in a tiny bit of Gibbs free energy today. There's your equation. I think that one lady who I talk about calls it the granddaddy, okay? I want delta G negative. So if delta H is negative, and temperature is whatever it is, and this is negative, you do not want the entropy to be almost too organized or too negative. So you want to say the enthalpy is driving this reaction. Now, which case is this? Temperature high or low? Keep temperature low, right? Okay, now how low? I know we're going to go over, but I don't care. This is worth it because this is a tiny bit of thermo. Here we go. We're going to solve for it, okay? So if somebody said, what is, and I'll have to just tell you the delta S, I'll explain how I got it, but I'm just going to tell you it. What if you were asked what's the temperature that would be necessary to make this reaction spontaneous, okay? Or what do we call it? Favorable, okay? Feasible. Here we go. So I'm going to keep that up here. I'm going to erase this other stuff. So the delta S, I would have had to look up all the numbers, okay, in a table, and I would have had to use the summation of products of that minus the summation. Oh boy, that's ugly summation, so I don't care. Here's what I got, okay? So here's the final answer. It was negative 543 joules, ding, 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 per mole per Kelvin. Joules. And negative. It was negative, very negative. Okay, so how are we going to solve for the temperature needed? This is where I was saying you make delta G equal to 0. So then you have 0 equals delta H minus T delta S. You have negative delta H equals negative T delta S. Move these over. And then finally you have that, okay? So let's just solve for that really quickly. I'm going to go up one here. And you might, I want this to kind of make sense at the very end. So our H was, now be careful, this was actually per 2 moles. So what would it be if I had per 1 mole? Here's what I got. Where was it? Right there. Negative 826 kilojoules for every 1 mole of this Fe2O3, okay? So that means the delta H is actually negative 826 kilojoules per mole, okay? And then we're going to divide it by S, which you just have to trust me, was, I think I missed a sign here. Where's the numbers here? Oh, the negatives will cancel. So then 0.54 kilojoules per mole. And I'm going to go like 1 over Kelvin. Okay. These are going to cancel. I move this over. These are going to cancel. And then Kelvin's going to end up coming up to the top. And here's what I found. I'm just going to go for it here. That's the answer I found. So what does that really mean? Or actually, I think it was 521. I need 1,520 Kelvin or lower to make this reaction spontaneous. As a human being on the face of this earth, what are you saying to yourself? Is this reaction going to be spontaneous at temperatures that I'm going to live at? Yeah, right, Dane? Yeah. What's like room temperature? 298 Kelvin. So this is going to be spontaneous at any temperature that we're ever going to think of. Which means, if you have iron, will it rust? Yep, it's going to rust on you. Okay. It's thermodynamically favorable. Okay. Not fast. There we go. My students are ready to tell me the answer. Not fast, probably. Because what's slowing it down? What are the 2 words? Activation energy. Okay. Bless you. Good time to sneeze. Okay, I was like wigging out there. So, this is upside down. So here we go. What I'm going to do is I'm just going to turn this around and I'm just going to try to show you the answer because we are at about 1 hour and 15 minutes. I think we're probably sick of this. So let's say they had you try to solve for, in this case, I think it wanted you to solve for the sublimation energy. So here's the question. I'll kind of just turn it around and show you the answer, and I'll talk about it with my students if they really want to. I don't think it's very likely. So you'd have to kind of think about all the energies that are going in and coming back out. Lattice energy is actually going to be negative because it's going to release because the ions are going to attract. We do know the total change, but we're trying to find this one cute little step about getting the lithium to turn into a lithium gas, like a heat of vaporization almost, but it's called sublimation. And in the end, we find that it's negative 181 kilojoules per mole. Let me just cover up the number. You don't need that number, but that's how I how I did the math. Okay, so that's that one. What I like about this one, though, is it ties back in lithium losing electron, ionization energy, diatomic iodine being broken, which is bond energy, iodine gaining electron, which is electron affinity, and then the lattice energies of these two, which are not super impressive. Lithium's kind of small. Where is it here? But iodine's kind of big. So I don't, their lattice energy is not that, it's pretty impressive, but because the iodine is such a large molecule, or ion, I should say, it's not going to be huge, okay? Remember, what affects lattice energy is charge and size. You want large charge, small size. Very energetic lattice energy. Awesome. I'm just going to ask the questions to my students and see if they have any. So you guys have any questions quick that you want to add just to the world of, chemistry? We have 5 people who are watching right now. I don't know who they are. Oh, Kylie's 1. So we have 4 other people. But any questions you guys have? All right. If I run a session 8, it will be kinetics, and it will be on Wednesday if we do it from the same time. If we want to, if not, it won't happen. So you'll know. But that'll be kinetics. So see you later. Thanks for watching. Hopefully, good luck on your AP exam. My students, I hope, are going to kill it. We're all going to pass. That's what we're going to put out there in the world. We're passing. We're all passing this exam.